to everyone. At the outset, let me thank Professor Gajendra Deshpande, my good friend, for giving me this opportunity to be with you, sharing some thoughts on NumPy, okay, which can be used for data analytics. Okay. Well, in the given time slot that is available to me, that is 45 minutes, I'll try to cover some of the aspects of NumPy uh, and hope everyone has Python background. So NumPy is a Python module for working with arrays. Okay. NumPy stands for numerical Python, and data analytics is basically analyzing the data available in two-dimensional form, which is having certain number of rows and certain number of columns. And NumPy is a powerful package available in Python, using which we can perform data analytics very quickly. Okay, you can also use Python lists for that. However, NumPy is more powerful. As I progress along, I'll probably demonstrate how NumPy is powerful compared to Python lists. NumPy is used to perform mathematical operations on arrays, and more importantly, the core of NumPy is powerful optimized C code. So the arrays are implemented using C. That is why it is more powerful. And NumPy is an open source library. So whenever I talk about open source, there are many contributors, and whenever I am in doubt, I can just post my query, and there will be more than one answers to the query. So NumPy basically makes use of lesser memory. So lesser memory consumption than Python lists. Implementation of multi-dimensional arrays is possible. You can go beyond 3 dimensions also. NumPy arrays are faster than Python lists. NumPy can be used to transform the arrays pretty quickly. And Python doesn't have inbuilt support for arrays. And NumPy offers functions like reshaping an array or sorting an array, reversing an array, and so on. Okay. The fundamental aspect of NumPy is ND-array. ND-array is a multi-dimensional array object, which is a container for homogeneous data. This is very important because compared to the Python lists, lists can hold heterogeneous data as well, whereas ND-array is for homogeneous data collection. That is, elements must be of the same type. And every array has a shape, a tuple indicating the size of each dimension, and a D type, which indicates the data type of the array. Okay. It supports different data types like int16, int32, float, 64, and so on. So as I said, you can create different dimensional arrays using NumPy, be it a one-dimensional array. Okay, as the screen shows, okay, this is a one-dimensional array having the shape as a tuple indicating 4. Okay, that is, it has 4 elements, or it's a vector having 4 elements. A two-dimensional array, okay, its shape as is seen on the screen is a 2 by 3 array. Okay, rows indicate axis 1 and columns indicate, or rather rows indicate axis 0 and columns indicate axis 1. Similarly, three-dimensional array, okay, which can be visualized as array of two-dimensional arrays, okay, whose shape in this case is 4 by 3 by 2. That is, there are 4 rows, and associated with each row, there is a two-dimensional array having the dimension or shape as 3 by 2. So, so I said NumPy arrays are faster than Python lists. Okay, why is that so? Is essentially because NumPy arrays are implemented as C arrays. And as you know, arrays in C are allocated memory contiguously. It's a contiguous allocation of memory. And NumPy uses fixed type. That is, the elements must be of same type. If you look at an element to be stored in a Python list as well as in a NumPy array, okay, its binary representation is this, okay, which is stored in case you decide to have the D type as int32 or yeah int32, then it will be represented as a 4-byte data as this. Whereas each element of a NumPy, Python list is an object by itself. Okay, list elements are objects by themselves, and every object will have its size, its reference count, the object type, and object value. Okay, the object value is represented as a 8-byte information. Then object type is another 8 bytes, reference count is another 8 bytes, and the size is, assuming the size is int32, then it will be 4 bytes. So effectively 28 bytes are required to represent 5 as an object on a Python list, whereas you just require 4 bytes. And in case I have more than one element on a Python list, then you may not be allocated memory contiguously. Okay. However, come to NumPy arrays, array elements are allocated memory contiguously. That is one aspect of NumPy arrays. And whenever we say that the elements are allocated memory contiguously, definitely the iteration or traversal through the elements of the array becomes faster compared to the objects which are allocated memory in a non-contiguous fashion. So as I said, NumPy arrays are allocated contiguous memory, whereas lists are allocated memory that is not contiguous. Python lists are resizable and can contain elements of different types. Okay. Whereas NumPy arrays have fixed type at creation and contain fixed type data. Okay. Does that mean NumPy arrays cannot grow? Yeah, you can definitely make NumPy arrays grow by appending or inserting elements and creating a new NumPy array. And more importantly, there is no type checking required when it comes to NumPy arrays because all the elements are of similar type. Compare that with lists. Okay, every element that I encounter on the list, I need to check what is its type. Is it an int or is it a string or is it a float or is it an object? And accordingly, I need to process that. And even during the traversal, the NumPy arrays are faster compared to Python lists. Okay, let me quickly demonstrate. Okay, by using the Jupyter notebook as to how NumPy arrays are faster than lists. Only when you appreciate the fact that these are faster and more powerful can you use NumPy arrays for data analysis. Okay. So let me quickly import the module called time and also import NumPy as an alias named np. Then let me create a Python list of around 1 lakh elements. So let me use, okay, is it seen? I need to share that, I think. I think it is visible now.
Yes, sir, it's visible.
Yeah. So let me create a list using list comprehension. Okay, the list will have 100,000 elements. And let me create another list of the same elements. So I have created two lists, L1 and L2. Okay, these are Python lists containing 100,000 elements. And let me also create a NumPy array, okay, having the same number of elements. Okay. Arange is one of the method available on the NumPy module, using which you can create an array having elements in the range 0 to 99,999 in this case. So I have created two arrays, and then let me add both the lists and let me add both the arrays, and let me find out how much time does it take to perform addition of all the elements of the two lists and addition of the elements of the two NumPy arrays. Okay. So let me note down the current time. Okay. Okay. The time module's time method gives me the current time, and then resultant list will be, okay, I'll again use the list comprehension for x comma y in retrieve each element from L1 and L2. Okay. Zip will give me each element of L1 and the corresponding element of L2. It will be assigned to x1 and x2, and those will be added, and that will be pushed into the list. And then let me display a message list addition took. Uh, I'll note down the current time minus the time that was noted down earlier. Let me multiply that into 1,000, so many milliseconds. Okay, so this will perform the list addition, this, and then I displayed the amount of time it took. Similarly, let me note down the time again, and then I'll add the two arrays, and the resultant array will be assigned with A1 plus A2. Simple as that. You just have to use the addition operator. Individual element of array 1 will be added to the corresponding element of A2, and the result will be stored as the corresponding element in resultant array. And let me display the same message again as to how much did it take. If I execute it, you'll observe that list addition took 38 milliseconds, whereas list, okay, there is a typo. This should have been array. Okay. So it says list addition took 37 milliseconds, whereas array addition took hardly a second. Okay. With this, you can understand how quickly the array elements are traversed in case of NumPy arrays compared to that of the list elements. So that is why NumPy arrays are faster than Python list. Now, how do I create arrays? Yes. Okay. So there are different ways of creating arrays. Okay. There are different methods. Okay. Array is a method which can be used to create an array. Okay. This will create a single dimensional array. In case you want to create a two-dimensional array, then you need to supply it as an array of or a list of lists. Okay, for example, np dot array 1 2 3 4. This will give me a vector. Okay? Whereas np dot array 1 2 3 4 5 6 7 8 9. This will give me a two-dimensional array having 3 rows and 3 columns. This is one way of creating arrays. So every time I need to share a PowerPoint presentation, Gajendra, I just cannot say Alt Tab.
I think you can, sir.
No, but Alt Tab is not working here. I don't know. I wanted to go to PowerPoint, but anyway, I'll just
Okay,
go on discussing these things.
sir.
Resume is share. Okay, fine. Uh, Zeros, okay, is used to create an array containing all zeros. Okay, this will create a vector, whereas this will create a 2D array having a 3 by 4 matrix having all ones. And I will create an identity matrix of 5 by 5. Linspace will linearly space the elements in the range 0 to 100 as a vector of 6, and a range, which we just used, okay, will create an array having elements in the range 0 to 10, and 3 elements are picked. Full will create an array of this dimension, and random, okay, it will generate a random array of 4 by 5 dimension. Okay, this will create a random array of floats. Okay, whereas randint will create a random array of integers in the range 0 to 5. Okay, it will create an array of 2 by 3. Okay, so you can inspect the properties of an array using these different properties, like size, which will return the number of elements in the array. Shape will determine the shape of the array, that is the number of rows and columns. Okay, D type will give me the data type of the elements of the array, and as type will convert the element to the specified type. In case I have created an array of int 32, but I decide to use int 16, then I can always convert the given array to int 16 array using as type. And toList is a method available using which I can convert a NumPy array to a Python list. Let me quickly demonstrate these. Okay. Let me create an array mp dot arange 1 to say 25. Okay, this will create an array of 24 elements. Okay. What is the shape of array? It is a tuple having 24 elements. What is the size? Size is 24. T type is int 32. That is by default. Okay. But I can always say a dot as type int 16, and b will be this, but the D type has changed to int 16. And I can always convert the 4 elements into a 3 by 8 matrix or 3 by 8 array having 3 rows and 8 columns in each row. So as you can see, the given array, which was initially a vector, has been reshaped as a 3 by 8 array. Okay. Similarly, I have methods available for copying, sorting, and reshaping an array. np.copy will copy this array to a destination. Okay. Uh, if I just say, okay, A is this now, okay, or rather, let me create a new array. Okay, A is this. Okay, it's a vector containing 10 elements. Now, if I say B equal to A, what happens? Okay, here A has been copied into B, but is that so? Okay, B is this, fair enough. But if I say B of 0 equals say 99, and if I display the contents of A, B as well as contents of A, you will be pleasantly surprised to know that A has also been changed. Okay, the first element of A has changed from 0 to 99. That is essentially because this has resulted in a shallow copy. Okay? Shallow copy in which B just becomes a reference of A, and any changes that you make to B will be reflected back upon A as well. Okay, so while assigning an array to another array, you need to be careful as to whether you want to perform a shallow copy or a deep copy. In case you want to perform a deep copy, then you have to say b equal to np dot copy A. Now B is this. Okay, A is also the same, but in case you want to change the first element of or the second element of A, look at B and A. Okay, B has changed, but the first element of the second element of A remains unaffected. That is essentially because when I use the copy method, it performs a deep copy, whereas if I just assign an array, it performs a shallow copy. The next method available is sort, which will perform in-place sorting. And just to quickly show it, okay, uh, a dot sort will give me the elements as this. A is this, and a dot sort gives me the elements in ascending order. Similarly, you can flatten a two-dimensional array to a single dimension using flatten method. Okay. T gives me the transpose of a given matrix. Okay. For example, A equals to np dot a range 9, reshape as a 3 by 3 matrix. A is this, and A dot T gives me the transpose. Okay. So look how simple is it to perform such operations using NumPy. Okay. So we just created a two-dimensional array, and I just said A dot T, it gave me the transpose of the original array. Okay. However, the original array remains unaffected. Okay. In case you want to store the transposed array back into itself, then probably you have to assign it. Okay. Only then A gets changed, okay, from this to this. So this is painful to switch between tabs. Reshape we just observed. Okay, reshape is used to reshape two-dimensional array without changing the data, and resize will be used to reshape existing array to a different dimension and fill the new values with zeros. Similarly, adding or removing elements from a NumPy array is pretty simple again. Okay, you have methods such as append, okay, which is used to append elements onto an existing array, insert, okay, which takes a position where it needs to be inserted. This is the index where you want to insert the values to an existing array. Delete will take the index and then deletes the element at that position, rearranging the array. Okay. And access parameter will take into account whether you want to delete it based on row or column. Okay. Just to quickly demonstrate these things, let us say this is A, fine. A dot append, okay, rather np dot append A, comma, okay, the value that you want to append. For example, you want to append 378. Okay. Then okay, 036, 147, 258, and 368 has been appended at the end. Okay, and of course, this appended list has to be reshaped so that it becomes an array. Okay, this has become a list now. Okay, or a vector. Okay, you need to reshape it so that it becomes, okay, a 4 by 3 array. Okay. There is a, it's not 4 by 3. Okay. How many elements will it now have? Well, oh, I just appended it again. So it has to be 5 by 3, or rather now, okay, it will be now a 5 by 3 array. Okay, because existing array was already 4 by 3. So when I appended a new row, then it becomes the new element. Okay. Similarly, if I specify access parameter as 1, then it will the column will be added. Okay. So column has how many elements? 5 elements. So I need to specify 5 elements, and then I need to specify the reshape as 6 by 3. Okay. So this will append this as the new column. Okay. Similarly, the insert and delete operations. Okay. Let me take a single dimensional array to demonstrate this. Okay. A is this, and A dot insert, okay, or other np dot insert A, comma, at index 1 I want to insert 99. Okay. So at index 1, 99 has been inserted and the remaining elements have been pushed to the right. Similarly, np dot delete A, comma 1, this will remove 99 which was initially inserted, and the remaining elements have been pushed back. 99 1. You can also perform scalar mathematics on NumPy arrays pretty easily. Okay, when you say add 1 will be added to each element, subtract, specified value will be subtracted from each element, multiply. Okay, so this will work on a single dimensional array. Okay, so each element will be multiplied with 3, or each element will be divided by 4, or POW, which will, okay, each element will be raised to the fifth power. Okay, as a dot add 1. Add a comma 1. Okay, a is initially this, and after doing this, okay, the elements will be added with 1. Okay, similarly, np dot subtract a comma 2. Okay, 2 is subtracted from individual elements. Similarly, np dot multiply and divide. This is about the scalar math that you can perform. Similarly, you can also perform vector math, which works on two arrays. Okay, add, okay, will add the individual elements of array 1 with the corresponding element of array 2, subtract, multiply, divide, power, array equal will return true if these two arrays have the same elements and have the same shape. SQRT will find the square root of each element of the array. Sign will give me the sign of each element. Log will give me the natural logarithm. Absolute, seal, floor, round, all these are possible on the NumPy arrays as vector math operations. And you can also perform statistics on NumPy array. Okay, like mean will give me the mean of the array. Sum will give me the sum of all the elements. Min will give me the minimum element of the array. Max gives me the maximum element. Var gives me the variance, and std gives me the standard deviation. Probably I'll just show this before we I wind up this. A dot min, a dot max, a dot var, a dot standard deviation. Okay, this will give me 4.5 as the mean of all the elements, 0 as the minimum element, 9 as the maximum element, 8.25 as the variance of all the elements, and 2.87 as the standard deviation. Okay. I think I'll stop here and welcome any questions if you have. In case anyone has any questions or anything to contribute, or PyTorch arrays also similar to NumPy arrays. Well, in fact, Python provides us with different variety. Okay. In fact, when I said Python doesn't support arrays, that's a misnomer, because there are various contributors to Python community, and in fact, Python has array as a module now. Okay, using which you can work on Python arrays also. Okay, same is the case with PyTorch arrays also. So, in case you don't have any further questions, thank you so much for the patient hearing, And thank you, Gajendra, for giving this chance to be part of this Belpai conclave. I think I'll stop sharing my screen now.
Thank you for the amazing talk, sir.